Hey guys, welcome back. This time around, we're going to take a look at the neurophysiology. If you recall from the anatomy components, there are two types of cells in the nervous tissue. There are the support cells and the neurons. Here we're going to take a look initially at the neurons. Now, the neurons, if you recall, are highly irritable. That means that they're capable of recognizing a stimulus, and if that stimulus is strong enough, they're capable of sending an electrical event down the surface of their axon. Now, this electrical event is known as an action potential, and the action potential is the mechanism that regulates all the fundamental activities of the nervous system. Now, before we take a look at action potentials and all the other players associated with neurophysiology, we need to first back up a moment and look at a little bit of physics. In particular, we need to take a look at the basic principles of electricity. Now, we're going to use this illustration here to help us to work through some of the concepts of electricity. Now, the body as a whole is net neutral. That means we don't walk around shocking folks because we don't have a net charge to us unless we have static electricity. But in localized regions in the body, say at the plasma membranes, we do have net charges. And those net charges can be either positive or negative, depending upon how they relate to a neighboring body part. Now, from this image here, you can see that on the outside of the axillema, it has a net positive charge in relationship to the inside of the axillema. Now, appreciate that that is a very narrow region right along the surface of that axillema. Now, this does specifically occur in plasma membranes that we do identify with a suffix called lema. So you find it in the axillemas, you also find it in sarcolemas, which are the muscle plasma membranes. Now, these separated charges of opposing values are going to be what we would think of as potential energy. And we can measure it using something called a voltmeter, as you see here. A voltmeter is going to be a tool that can measure voltage. Now, voltage, by definition, is going to be potential energy. It's what is in there that is capable of doing work. We've got a battery, we've got opposite poles, and we can use a voltmeter to measure the voltage, the potential charge on that battery. Same concept here, except we'd use much smaller probes to do it. We would use what are called microelectrodes to measure the voltage. Notice here this voltage is measured as a negative 70 millivolts. Now that's negative because we typically look at the inside and compare it to the outside when we're looking at voltage. Now, voltage is always going to be a measure between 2 points, and it's going to be measuring the potential energy, and it's going to be greatest where the difference is greater on either side of a membrane. So the greater the difference on the positive side versus the negative side, the greater the voltage. That's true of a battery if you think about it. The stronger the charge is, the greater the difference is on either side. Now, when we put the battery to work, we are creating what's known as a current. And that's true in the human body as well. When we allow these positive and negative environments to be altered by opening up the plasma membrane and allowing the flow of ions such as sodium and potassium, that flow is known as a current. Now, the stronger the voltage at rest, the stronger the current will be when it's allowed to flow. Now, since it's a movement of, in this case, ions, then that current is going to be what we think of as kinetic energy. Now, there is a direct relationship between voltage and current, but there's also one other player in talking about the strength of a current, and that's the resistance. Is there a resistance to the flow of those ions, or is there a resistance to the current? Any resistance to the current, the greater the resistance, the less the current. The less the resistance, the greater the current. So that's an indirect relationship. Now we've got an equation that allows us to calculate these things, and it's known as Ohm's law. Ohm's law says the current is equal to the voltage divided by the resistance. Now if you break that apart, that means that the current is directly proportional to the voltage. The greater the voltage, the greater the current. And it's indirectly related to the resistance. The stronger the resistance, the less the current, and vice versa. Resistance is typically going to be described as two types of resistors. Those can be insulators and those can be conductors. Insulators are going to have high resistance, and so very little current flows through them. Insulators are things that we would use on electric fences, if you think about it. In our body, we would think of them as myelin sheaths. And conductors are going to be things that would allow the current to flow with very low resistance. Now, we would find those if we looked at the telephone pole, I would imagine. Now, in the human body, though, if we look at electrical current, we're talking about a flow of ions. And the resistance in the human body is going to be plasma membranes. Now, plasma membranes are going to regulate the flow of the ions. Most of the ions are going to be impermeable or minimally permeable to a plasma membrane. But embedded in that plasma membrane will be things that we call ion channels or ion gates. Now, these ion channels are going to be composed of complexes of proteins. More than one protein making up these channels, but a complex of proteins that are going to be integral proteins that are going to be transmembranal proteins. Now, integral means they're embedded in the plasma membrane. Transmembranal means that they have exposing ends to them that are going to be in contact with the extracellular fluid, and other ends that are going to be in contact with the intercellular fluid. Now, these ion channels will support both passive and active transport. And there's typically two types of ion channels that we can discuss: chemical and voltage regulating channels. Now, a chemical gated ionic channel opens by being stimulated by a specific chemical. Notice here in this image that what happens is a chemical comes along and binds to the surface at a receiver site on that protein. Now, what kind of chemical can bind there? Well, it depends upon the protein itself. It can be anything from nicotine, caffeine to a hormone, but typically it's a neurotransmitter in the case that we're going to discuss here. Now, when it binds to the gate, it causes a conformational change in that protein. That conformational change, as you can see here, will open up a slight pore that will allow simple diffusion to occur. Now, remember, simple diffusion is going to be a movement of a particle. In our case, it's sodium and potassium from this image. And it's going to move from a region of higher concentration to a region of lower concentration through this pore. Now, the greater the difference on high and low, the faster it will move. The only limiting factor is, can it fit through the pore? So in this case, sodium and potassium can fit. The other type is voltage regulated. Now, voltage regulated ionic channels are going to be those that are going to be sensitive to membrane potential changes, such as something like depolarization occurring. Now, notice here we have integral proteins, but typically those integral proteins have embedded in them very sensitive regulatory proteins that can recognize a voltage change and cause the pores to open, allowing chemicals to move across them, whether those be ions, whether those be other things. Now, before we get too deep into that, it's also appreciable to know that what I'm calling a chemical gate here could be a chemical gate one moment and a voltage regulated gate again at another moment. We do have a series of these complexes that are found in the plasma membrane that can be sensitive to both chemical and voltage. So these aren't exclusive players. Quite frequently, they're overlapping players in regulating action potentials. Now, finally, as we're looking at these action potentials and the physiology, appreciate that what's moving across these channels as they move is going to be ions. Now, these ions are sodium and potassium most frequently, and they're going to move by simple diffusion from high to low. And so this is going to be a chemical concentration gradient then that allows the movement along a chemical concentration gradient from a region of higher concentration towards a region of lower concentration. Now, these same particles, though, frequently are charged. Now, let's say we take that sodium ion. Now, that sodium ion is a cation, as you can see, a positively charged ion. Now, let's say it moves into an environment that is negatively charged, as you see depicted here. Not only will the ion itself, the sodium, influence the environment, but the charge on that sodium atom will influence the charge as well, making the inside of that cell membrane less negative as more sodium moves in. Thus, a sodium cation moves into a negatively charged environment. It creates what we think of as an electrical gradient. So when we're talking about action potentials and other things, we really are talking about two phenomena that's occurring: a concentration gradient as well as an electrical We put those together and we say we're talking about an electrochemical gradient mediates the flow of ions and the effect of the flow of the ions across a plasma membrane. We'll talk about resting membrane potential next time and hopefully apply a little bit of this electricity and physics there. Be good. See ya. Be safe.